Hey guys, it's been a while since I've done any content. Life's been pretty crazy, but I'm back at her and I'm going to get some of these projects that I talked about in the last year rolling. And the first one I'm going to do is the Coco in an IBM PC case that I talked about in a previous video. Now, if you saw that video, I mentioned that probably the keyboard interface was the most difficult part of that. And the reason is that this keyboard on the IBM uses a serial interface, whereas on the Coco, it's expecting a matrix interface. So I'm going to have to build an adapter that will convert those two signal types. In order to do that, I'm going to use a microcontroller. I might use an Arduino. I got to think about this a little bit, but I'll be showing you how I'm going to build that. And I'm also going to show you in this video a little bit about how a matrix keyboard works and probably take a look at the interface on the Coco so you can get an idea of the electrical signals on that interface. I hope the video is informative for you and you enjoy it, and leave any comments below, and if you like my video, please subscribe.
Here's the keyboard matrix in the PIA, which is a peripheral interface adapter. On this there are two ports you can see here, 8-bit ports. So there's port A and port B down here. And you'll notice that port B goes into the columns on the keyboard matrix and port A goes into the rows. It's easy to imagine how this works. The electrical signal will come from one port somewhere, and then it goes via a switch here and is detected on the other side. Now, it's not quite that simple. There's a little bit more that goes on to make this work. What happens is that the B port is set to high. Each of the lines are set to high, and in turn each line goes low. So this one will go low, this one will go low, this one will go low, etc., etc. And it just keeps looping back and forth from 0 to 7, keeps on going through those iterations. Now, the reason that those are going low is because there's code in the system that is making it go low. So the code is actually rotating bits in order to make each of these go in turn. And I can actually show you that really quickly here in the source code. And if we take a look at the source code, here we load the PIA up, and we essentially we clear register A and we push that into the PIA, and then we rotate that PIA byte, so it goes through and the 0 rotates to each position in turn. This is constantly rotating, and then as it goes through the cycle, what happens is that the system looks for a low input on any of these input ports. So if, say for example, we've gone through 10, 11, 12, 13, now 13 is low. That low signal will go through, and if no key is hit, it actually won't go anywhere. But let's say the C key was hit. What will happen is that signal will go into port A, bit 0. So the code looks at the two pieces of information that it knows. It knows, because the code is setting the state of this byte here, it knows which port is currently low, this one right here, and then it also knows which inputs it sees that have that low signal on it, PA 0, bit 0, and it knows the only combination that can be is a C character. With a matrix keyboard, you can also hit multiple keys at the same time, although there are some complexities with it, and certain combinations of multiple keys will not work. Fortunately, the computer is typically faster than a lot of your key hitting, so if you hit multiple keys, there tends to be a few milliseconds delay, which is fast enough for the computer to distinguish them as two separate keys. But there can be situations where you slam on the keyboard and it won't pick up all the information, which is pretty acceptable in most cases anyways. But if we imagine this scenario where, say, we hit the S key as well as the C key at the same time, if PB3 goes low, the S key will also conduct, and it's going to conduct into bit 2 of port A. In this case, the system will be able to determine that there's the C key and the S key hit at the same time. Another example there is if you're hitting the Alt key while you're hitting these other keys. Again, bit 3 on port B goes through the Alt key, and then that goes to bit 6 on port A. So with this combination of bits, it will know that these 3 keys have been hit. Pretty straightforward system. Now, one thing that is worth mentioning is that when you're working in a retro computer, and when people were building these machines back in the day, saving a byte here, saving a few instruction cycles here and there, that was a big deal. You only had 64K worth of RAM total to work with in most of these machines, of which you might spend 32K you might have for the entire operating system and the default programming language, which is BASIC. So you really had to compact things, be very efficient with your coding. And it's interesting in the design of this keyboard, the way it's been designed. If you look at the ASCII key codes for each of these keys, this one right here is key code 64. The uppercase A is ASCII code 65. B 66, so on and so on, so forth. And it keeps going on. These ones don't line up. However, when you get to the exclamation mark, and all these keys up to, I believe, the question mark are all in sequence in the ASCII character table. And that actually explains one thing, which is why on the color computer, the 2 key has a quote above it, whereas in pretty much every other computer ever made, well, in the last 20 years anyways, the @ symbol is over the 2 on an American keyboard. So, kind of an interesting little factoid that this keyboard layout that has been designed and interfaced into this PIA has been designed specifically to be optimized for the ASCII character set, and by doing that they probably save themselves I don't know, 20 instructions, who knows, maybe more, and they save themselves 20 bytes. So it's just an example of where the architecture of the system was really optimized for high efficiency to get the most out of the code in the limited amount of RAM that they had. So in order to create this, I'm going to use an ATA Mega 32, which is from the AVR family of chips. The AVR family is what's used as the chip in the Arduino, and actually an Arduino is pretty much just an AVR chip with a couple of support chips for USB and whatnot on it. So it is more than anything else, it's just an AVR chip with some support chips and some bootloader code that they've provided. So this will let me, work in a familiar environment, work in the C language. It's quite easy to use. I may or may not use the Arduino bootloader, or I may just code directly the AVR. At any rate, what I'm going to have is I'll have the keyboard over here. So there's my nice keyboard. I did not pass art class, as you might imagine. That will connect into the RxD and TXD, transmit data and receive data ports on the AT Mega 32. And then I'll probably end up using one of these other leads here in order to manage the clock signal, and then I'll also need to give 5 volts over to that keyboard. So the keyboard's going to be wired into there. On this side, I've got port A and port C, and these will connect up with port B and port A on the Coco PIA. So, excuse my horrible drawing here. This is the PIA. And basically on port B of the PIA we have our strobe signal. So let's actually draw that down here. It's closer to reality. So port B, the strobe signal goes to these pins here. And remember, this signal has all these pins as high, except whatever's being strobed goes low while it's being strobed. And then on this side, what I'm going to have is an output which emulates what the output should be if it were actually the matrix keyboard. It's going to emulate that. So if the ACT key was hit while the strobe zero was low, I would make this line low, at which point the PIA knows that it was an ACT key that was hit. So in order to handle that translation from a software perspective, this keyboard here will, when a key is hit, there'll be the make code and break code. I'll use the serial input, and I'll likely use an interrupt routine. So interrupt routine is a routine that is called based on a particular signal, and I can set up an interrupt on the serial. And what will happen in that interrupt routine is that the code that comes through here, let's say it's a Q, which is a code 16. That 16 code will be in memory, and I'm going to move that over into a memory array. So the memory array emulates the matrix keyboard layout. So you've got 8 bytes by 8 rows. Yes, I'm not going to draw 8 rows, but you get the idea. So a 16, which is a Q, will map into the Q space on the keyboard, which is going to be, let's say, somewhere around here. Now that I think about this, this may be able to be mapped just as single bits within an array. So it would be 1 byte here, so a char type, char, and I'd have an array of 8 of them going down to represent each row. What will happen is when the system sees the strobe state at a certain state, it will look in this memory array, and it will say, okay, well, strobe 0, nothing, strobe 1, nothing, strobe 2, here we have bit 4 is set, and that will fire bit 4 to low on the PIA side. So the PIA on the Coco should be able to handle it from there. So that's basically the concept of how the software will be architected at a very high level. One thing worth noting is that even though, you know, the sampling rate on the keyboard isn't that high, there's a very good possibility of losing some data. So I needed to do a little bit of double checking to make sure this was possible. I measured the rate of the strobe. So I took one line and measured the strobe rate, and I got a rate of 150 hertz. There's 8 lines, so 8 times 150 is 1200 hertz that I have to worry about. That's my sampling rate. And using a Nyquist number, multiply that by 2, I need a sampling rate of at least 2400 hertz. I know that the ATmega 32 can only sample about 10,000 hertz, 10 kilohertz on the analog lines. I'm not quite sure what the digital lines will do, but I know that the analog lines are only at 10,000 kilohertz, or sorry, 10 kilohertz, which is only 4 times this number. And what that means is that I'm going to actually lose data because I just don't have enough bandwidth here. What does this mean if I have 10 kilohertz sampling? If I use the Arduino digital read API and I look at each pin in turn, if I can only do a 10 kilohertz read on these individual pins, what's going to happen is I'm actually going to run out of bandwidth at the 4th pin. I will start losing data at that point, and it won't be reliable. So in order to read this, I'm going to use a different approach, which you may have seen if you're an Arduino guy, which is reading the entire port at once. So I can go port C, which is a macro, and I will get the binary 1 byte value for whatever the state of these pins is. So let's say that state is, you know, hex 11114, and that will equal, you know, a certain code in binary. I don't know what that is, but 101010, and that will determine what pins are hit, and I can read that in the same amount of time that I would do a single digital read. So that should give me the bandwidth that I need in order to reliably read these lines as they go along. And the ATmega32 runs at 16 megahertz, and the Coco only runs at 0.89 megahertz. So you would think there'd be plenty of bandwidth to read this data reliably, but it's something to be aware of, that you may or may not have the bandwidth you're expecting. So it should be, you know, you should determine in your designs whether it's going to be possible or not. I think that by reading the port in one single read, I should be able to do this. I'll need to do a little bit of experimentation to make sure that's the case.
This is the start of the little board that I'm going to use to build the keyboard interface. There's a 40-pin socket there for the ATmega. I put some current limiting resistors there just in case. I don't know if they're strictly needed, but I thought that maybe during boot up there's a possibility that there could be excessive current, so I put them in anyways. There's a header here that will plug into the Coco motherboard, and then I also have a header here for power and for the serial interface from the IBM keyboard. Now I'm going to connect the logic analyzer to the Coco motherboard so we can take a look at these signals. So here it is all connected up. We've got the logic analyzer connected, and we'll power it up. Starting now, and we should get some boot info on the screen, and copyright 1992. This is a pretty good little unit. It's old, but it's fine for, you know, slow speed digital logic. Okay, that's no good. I tried for about 20 minutes to get this to work and couldn't get a good display. Didn't have any luck with the logic analyzer, so I decided instead to use my oscilloscope. So I plugged in channel 1 and channel 2 into the Coco, and I put those onto line 14 and 15 of the keyboard interface. So this will show me the timing when that strobe line goes low as it cycles. Unfortunately, I've only got 2 channels on my scope, so you can't see the whole picture, but it should give you an idea of what's going on. Okay, so I'm going to turn the Coco on, and you can see the keyboard lines there. This is line 14, and this is line 15, and you can see that line 14 is pulled low, then it goes high, and then immediately after, line 15 goes low, and then it goes high. If I zoom out, you'll see that these things stay high most of the time. One other interesting thing I noticed is that if I turn the machine off, then I power it on again, there's a bit of a delay between powering it on and the signals coming up. And the reason is because the Coco is running its initialization code in ROM, and the keyboard cycling is part of the code that I showed you earlier, and it doesn't actually start until, you know, half a second after you power up. Well guys, that's about it for this video. I hope you guys enjoyed it, and if you like what I'm doing here, please subscribe. I really appreciate the subs, and thumbs up if you like it, and I'll see you guys soon.